Welcome back. We're continuing, and in segment number 2, we begin to look at moment of force and mechanical advantage. When the sum of turning moments, okay, or what we call torque around a rotational axis is 0, a state of dynamic equilibrium is reached. Now let's look at an example here. Tembi of mass 50 kilograms and Musa of mass 70 kilograms are sitting on either sides of a seesaw. They want to keep the seesaw balanced. Musa is sitting at a point 2 meters from the pivot. Where should Tembi sit so that the seesaw could be balanced? Okay. Now, the sum of all the moments of force here should give us 0 to be able to have a balanced seesaw. Okay? And then from here we can be able to say, okay, what is the total here? We've got, if you like, you can draw this here. Say you've got a pivot there, and Musa is sitting 2 meters. So from here, 2 meters, Musa sits there. There is Musa. Okay? And then we want to know where Tembi will be sitting. Okay? Let's say Tembi is sitting somewhere there. We want to know this. Okay, this distance here. So it will mean that this total, it will be equal to the force as exerted by Musa times the distance from the pivot for Musa. This is for Musa, plus the force on, as exerted by Tembi times the distance for Tembi. Okay. Now, all this should give us 0. So you've got 0 equals, for Musa, look at it. Musa is 2 meters away, and Musa, the mass of Musa is 70. So remember, this is working from the forces of gravity, or their weights. So this will be mg delta x Musa plus mg delta x Tembi. This is all for Tembi. So let me put it this way and say Musa Tembi. Now this should be equal to, for Musa it's 70 times 9.8 times Musa is 2 meters away, plus for Tembi we've got 50 kilograms times 9.8 times delta x is what we're looking for. We want to know how far Tembi is from the pivot. Okay, now what we will do here is, let's work it out. So this equals 0. We've got 70 times 9.8 times 2. Okay, so this is equal to 1372 plus 50 times 9.8 is 490x delta x. Okay, this is equal to 0. Therefore, 490 delta x equals minus 1372. That should be equal to, so delta x equals 1372 divided by 490. And what is that? Okay, divided by 490, and the answer is 2,8 meters. But remember, this is minus, so this is minus 2,8 meters. This means Tembi has to be 2,8 meters on the other side. The negative sign just simply tells you on the other side of the seesaw. Okay? Quickly looking at mechanical advantages, a mechanical advantage. When we have levers, we would have to know how effective those levers are, and to measure that we make use of mechanical advantage. So any device or machine that increases the applied force or the distance between the pivot and the point at which force is applied is called a lever. So that's what a lever is. In levers, the applied force is called the effort. That's very important to note. And the force that is to be lifted is called the load. Okay? Now, the load is usually given by the weight of that object, because most of the time we are lifting things up. So the weight of that object becomes the load. Okay. Now, the effectiveness of the lever is measured through the mechanical advantage of that lever. How do we work that out? Mechanical advantage is given by the load divided by the effort. So mechanical advantage is equal to load divided by effort. Okay. Now, if you don't want to use that, you can say you can use the arm section. So the arm divided by the load arm, the effort arm divided by the load arm. And if you were to do an example here, which I don't have time for, you can see this becomes, Suzanne applies a force. This is effort. Okay, Suzanne wants to lift this thing, this crate up. And then the crate is 60 kilograms. From that you get your load. Okay, so you can calculate the mechanical advantage as using load over effort. Okay, and from here it means you will say the load is 60 kilo. Allow me to use 10 there, so it's 600 divided by 240. And if mechanical advantage is greater than 1, then the effectiveness of that lever is good. Let's meet in the next section.